Who said yes?
Yes, you mind, or yes, please start early?
She said that. You want me to start early? Oh, that's a different, that's a different response. I don't think there's going to be anybody else showing up, and even if they do, they're not going to miss that.
But the folks who are here won't mind if you start early.
No,
That's almost
I'm covering at the beginning something that has nothing to do with the actual operation. Well, it has everything to do with the actual operation. Okay, so welcome to the Computer History Museum's presentation of Babbage Difference Engine No. 2, Serial 2. That's its official name. And the first three words of that are Babbage Difference Engine. Babbage was the name of the gentleman who actually created this thing, designed it. And that's his photograph there hanging in the center panel. Based upon his age in that photograph, I'm guessing it was taken sometime in the late 1840s. Definitely before our Civil War, but it was taken in London. The third word in that title is an engine. Okay. And I have a definition for an engine. It's something like this. An engine relieves you from having to do the work. Now, Fred and Barney Flintstone used to go out to their little vehicle and they'd get into it and they put their feet all the way down to the ground because there were no floorboards. And they grabbed onto the sides of the vehicle and they ran with the vehicle. They were the engine. This is an engine in the sense that it relieves you from having to do a different kind of work. It's mental work. It does calculations for you and it does them rather quickly. Okay? It solves polynomial equations. Not for what's the value of x when the result is 0, but for various values of x, what do we get for a result? Okay? And it does it very quickly. We get a new answer out of this machine about every 8 seconds. It's mechanically operated. It's doing a 7th order polynomial, which is an x to the 7th. But to give you an idea of what it's doing and why, I'd like you to take a look at the blackboard. We're starting. Okay.
Yeah.
So if you back up a little bit so you can see the board clearly, I don't mind if you crowd it over here, it's fine. I'd like you to take a look at the equation on the upper right, x cubed minus 2x squared plus 1. Very simple polynomial equation. You probably saw these back in high school. Now, if you put various values of x into here, you get a series of answers. Let me give you an example. When you put x equals 1, you have 1 cubed is 1. 1 squared is 1, times 2 makes it a 2. With a minus sign makes it a minus 2. So we have 1 minus 2 plus 1. And when you add it all up, you get 0. So for x equals 1, the answer is 0. When you put 2 in there, 2 cubed is 8, 2 squared is 4, times 2 is another 8. 8 minus 8 is 0, plus 1, so the next result is 1. Simple. Put 3 in there, you do not get 2. Don't get misled by 0, 1, it's not going to be 2. 3 cubed is 27. 3 squared is 9, times 2 is 18. From 27 is 9, plus 1. You get 10, and then 33, and then 76, and 145, and 246, and on and on and on it goes. Okay? Now that we've got this result for this polynomial equation, this is what they've discovered. And this is where the third word in that title, Babbage Difference Engine, comes in. Can anyone tell me what they think the term difference means in that title?
Differential equation.
No, not differential equation. Difference, not differential.
Is it the interval between the successive results?
Well, so interval between successive results means you're doing something that we learned back in elementary school, the very first grade of math. Subtraction, and the answer is called the difference. When you get a subtraction, the result is called the difference. So yes, that's exactly what it is. So if I subtract 0 from 1, what do I get for an answer? 1. So I write that next to the 0. 1 from 10, you get 9. 10 from 33, you get 23. 33 from 76, 43. We get this column of numbers here, which is the difference of these consecutive results. Okay? So this column of numbers, however, is not random. They are, in fact, the results of another polynomial equation. which is written at the bottom. It's 3x squared minus x minus 1. Okay? And if you put x equals 1 in here, 3 times 3, subtract 1 and subtract 1 again, you get 1. And so on. Okay. Now, since this polynomial equation results in this set of differences, we can do the same thing we just did with the first polynomial. Subtract 1 from 9, we get 8. 9 from 23, we get 14. 23 from 43, we get 20. We get this column of numbers here. And they're not random. They follow the equation 6x plus 2. Okay, and you can prove that. 6 times 1 is 6, plus 2 is 8. 6 times 2 is 12, plus 2 is 14, and so on. Now, since this polynomial results in this set of answers, we can do the same thing again. 8 from 14 is 6, 14 from 20 is 6. We get 6, constant 6. Doesn't matter what x is. And we can do it one more time. 6 from 6 is 0, 6 from 6, everything to the right is 0. But it's not even written on the board. We didn't take the time to do that. Okay, so we get this table that we've created. Okay?
You can get infinite.
And they're called finite differences.
Yeah.
Yeah. Now, what can we do with this? Now, there's 4 complete rows here. I would like you to give me a number from 1 to 4. Who said 3? 3. The only, does everyone agree 3 is okay? Okay. It's the only card I have in my pocket. What's the point? Since the end of June of 2012, this is the only answer I've gotten. 3. I'm not kidding. You have a 1 in 4 chance of getting a 3. I've gotten a 100% response of 3. You can look at my pocket if you don't believe me. All right, so I'm going to take the 3rd row. Now watch this. Add 23 to 10. What will 10 turn into if I add 23 to 10? Hello? 33? The number below the 10? Add 20 to 23. What will 23 turn into? 43. Add 6 to 20. 26. Add 0 to 6. The 3rd row produces the 4th row. And we're not doing any multiplication. We're just doing addition. But we're doing a whole series of additions to get one row to become the next row and one row to become the next row. Now, Babbage knew about this and was thinking about designing a machine that would be able to do it, but he realized that it was very difficult if it was a x to the 99th polynomial, not just a cubic equation, but x to the 99th, which would have a result in 99 differences, 100 columns wide, that such a machine would be too hard to handle, to be able to do 99 consecutive adds across the board. So he had to come up with some way of being able to do it, number 1, faster, and number 2, simpler. And he came up with it. He simply groups the columns into odd and even pairs. He adds all the odd columns to all the even columns, and he does them all at once. But he can't do them straight across. He has to stagger them as steps. And so it looks sort of like this. I can add 6 to 8 and 9 to 1, and I can do them at the same time. So if I add 6 to 8, what do I get for an answer? And add 9 to 1, what do I get to an answer? So we get 10 and 14. Simultaneously. Now that we've created 14, add 0 to 6 and 14 to 9. Do the even and odd columns. When we add 0 to 6, we get? And add 14 to 9, we get? 23. We get these 2 answers. So now we're down one step. We can do 6 to 14 and 23 to 10, and we get those 2. We add 0 to 6 and 20 to 23, we get those 2. And even if it was 100 columns wide, with 50 steps, 1 complete cycle of odd evens and 1 complete cycle of even odds, and you have a new result. And you just go on and on and on, except you're doing things in parallel instead of doing them in series. This machine's working on a 7th order polynomial, so it actually has an x to the 7th equation. And I'm going to show it to you. Now, it's on the top of a piece of paper. And if I can say it in one breath, well, here we go. 8x to the 7th plus 2x to the 6th plus 9x to the 5th plus 5x to the 4th plus x cubed plus 7x squared plus 4x plus 41. Okay, and when x is equal to 0, the answer is 41. That's pretty simple. But when x is equal to 1, then it's actually the sum of all the coefficients plus 41, and so on. Okay,
Actually, it's currently 215 on this.
yeah, we're up to 215. Okay, so and I've got computer printouts of what the answers are. Okay, now, having seen what the odd and even columns look like over there on the blackboard, let's see what they look like over here on the machine, and then we'll actually crank it. You can see it run. This is an odd column. It's the equivalent of the diff3 column. It contains the constant that was computed. This is the last of the differences. This would be the diff number 6, and then 5, 4, 3, 2, 1, and the result column. So this is the result. This is the first difference, the second difference, and so on. Odd, even, odd, even, odd, even, odd, even. Result is even. The odd column has to add to the even column. We're going to do all odd, even pairs at the same time. Now, on the blackboard, when I added 6 to 8, and you said the answer is 14, I did not erase the 6. It was still there, because I had to do 0 to 6 as the next step. And when I added 9 to 1 to get 10, the 9 was still there, because we had to add 14 to 9 in the next step. So I did not destroy the numbers that was being added to the column that was getting the summation. But how am I going to get this column to add to this column? I have to destroy it. I have to read it. So what he does is he counts the odd column down to 0. And he transmits it through a gear in between to the column next door, which counts up. So one side counts down, one side counts up. The number that counts down to 0. We've now destroyed it. But we've got to restore it. So he lifts the gear that's between the two, 3/16 of an inch. It has on it the value that was transmitted to it. Okay. Now he has it go back to its 0 point, which means it restores the odd column back to its original value. Now why wouldn't that undo the even column? Well, because the gear in between is thick on one side and thin on the other. And on the side where it does the add and it lifts up 3/16 of an inch, it separates. But the odd side is still double thick. It's still connected. So we end up putting the odd column back to its original value. Then he lifts that gear up 3/16 of an inch again, and it completely separates from both the even and the odd columns. And the gear between the even and the odd drops down, and we start counting down the even and adding to the odd. Lift it up, 3/16, reset the even, lift it up 3/16 of again, disengage. The odd side drops back down to the bottom, and we start doing odd to even, reset the odd, and back and forth it goes. So it's actually, as an add step, there's a reset step, and then we're into the add step, and then the reset step, those 4 steps. Okay, and the adds begin when the disengage occurs on the opposite side. So they both occur simultaneously. And this is what it looks like. So here's the add, here's the reset, here's the next add, and here's the next reset, and we're back to the beginning again. And everything is changing in between. The only thing that doesn't get destroyed is the column on the end. It counts down and then it gets reset, but it never gets changed. Did it catch?
6.
Yeah, it's okay. I'm looking for the computer. Here we go. Oh, we at? Where are we? We are at 220. Okay, now I'm claiming x is equal to 220. How do I know that? From the 4th row up, not counting before 1, 2, 3, 4, the 5th row up, we're doing that 7th order polynomial. The equation is built into the columns from about here on up. The bottom 4 are doing another equation at the same time. R equals x, starting at x equals 0. Okay? So, the result is 0. Add 1, what's the next result? 1. Add 1 again, the next result. and you get a table 0, 1, 2, 3, 4, 5. Take the difference between consecutive results. You get 1, and then 1, and then 1. Well, you get a constant. Okay, so we put 1 into this column, zeros in everything else on the bottom, and every time we get to the point where we add this column to that column, it counts up by 1, and then it gets reset. And nothing ever changes it because everybody else is 0. So we're keeping track of x. So x is equal to 220. One of you ladies in the front, take a look at the 220th row. See it? I'm going to read the number that you look at, okay? I see 1997800408405877721.
Perfect.
Perfect, meaning it's the same thing you have on the printout?
It is.
That says that Babbage has just proven that our computer was correct. Or is it the other way around? They're both the same, and it had been the same for a long, long time. Babbage has designed a machine which will jam if it's beginning to get out of shape. We had a jam, and in fact, Eric was able to fix the jam, and we continued on. Okay, so it's got built-in safety catches to make certain it never computes an incorrect answer. What jammed in this case was the connection between this gear and the gears in the back, which we'll look at in a few moments.
It's a common thing if you go too fast.
Yeah. This machine is very cranky. It doesn't want to go too fast and it doesn't want to go too slow. It's got to go at exactly the right speed, and the load varies like crazy all over the place, which is why we have to have a human operator. Cranky. Okay. Now, why would someone invent a machine like this? What's it all for? And the answer goes back to what happened to Babbage in his early days. First of all, Babbage was born on December 26, 1791, the only son of a rich banker. His father was able to send him off to Cambridge University, where he went through the math school and got his bachelor's degree in mathematics. He did not go on to get any further degrees, but he stayed on with the university in a teaching role and a bunch of other things, including forming of intellectual societies. I'll get to that in a moment. At one point, however, he was nominated and became elected to the chair of mathematics at Cambridge. And it's a chair that's only been held by various other notable people, like Sir Isaac Newton, and most recently by Stephen Hawking, just to give you some ideas. So it was a very prestigious position. He was also involved, like I said, with the setting up of intellectual societies, and that gave them an opportunity to meet people like Charles Lyell and Charles Darwin and Charles Dickens, a lot of guys named Charles like him, and someone else named John Herschel. And Herschel was in the astronomy club, and he came to Charlie one day and he says, Charles, I've got this problem. We ran out of astronomy tables, so we went to a publisher to publish new ones. And in the process, he ran out of materials. He couldn't give us the complete set we needed. So we went to a second publisher to get more volumes produced. And now I've got these two different volumes from separate publishers that are supposed to be the same, but I don't think they are. Would you be willing to compare them with me? So one night, John comes over with these two volumes, and they sit down and they start going through them, and they begin to find discrepancies between the two. And they get to one page with so many discrepancies that it just annoys Charlie no end. He leaps to his feet and exclaims in a rather loud voice, "My God, I wish these values had been executed by steam," which was his metaphor for get rid of the human element in the development of these tables. Well, what was the human element? He had a library with over 300 volumes of mathematical tables. And he went and looked at some of them, and he realized all this stuff is being done by the method of differences, using polynomial equations that fit the curves for things like sines and cosines and logarithms and all kinds of stuff. And all that work was being done in France by unemployed French hairdressers. I'm not kidding. You can go look stuff on the web. Okay. Anyway, these French hairdressers, they were unemployed because of the French Revolution. I'll let you think about why you don't have hairdressers. You already know, don't you? The guillotine. Chopped off their heads. So what did they get trained to be? They trained to be computers. They're computing these tables. And they had multiple people working on one table at one time, so that one person gets an answer, another person's getting the same answer, supposedly. And they're using the method of differences, which is nothing more than an addition process. And when they're all done, they look at these two answers and say, they match. And the third guy, yeah, they match. They plug the equation in and make certain it actually matches on the last answer. And if everything is okay, then they go ahead and give it to a typesetter to print the page. Well, the typesetter doesn't know what these numbers are. Not only that, but he's working on a typesetting plate that he has to turn upside down, okay, so he can put the movable type into it. And so he's working right to left while he's reading left to right. And if you start reading a piece of paper and you're putting numbers in and you go back to the paper and you skip a number or pick up a number twice or even change rows, you're going to make a mistake. The answer is not going to be correct on that sheet. But then you turn the thing over and you print thousands of pages all with that same set of errors. And every book published had the same set of errors, a different publisher, different errors. With the publishing was the problem. So Babbage knew he could build his own typesetting machine to be able to solve that problem, but how are you going to feed it? Can't have humans feed it, that was the problem. So he has to design the engine that's actually going to produce the values that feed the actual typesetting machine. Well, he can't afford to do that. But then he notices in his volumes of tables in the library that a lot of these are government tables. There's things like navigation tables for ships' captains. There's tables for buildings and bridges and things like that, actuarial tables, all these various tables. So he goes to the British government and he says, hey guys, do you know that your tables are full of errors? And they say, yeah, we know. Well, what can we do about it? Well, I can build you a machine which will produce flawless answers. And he talks about what he plans to do and how it would work. And they thought it was a pretty good idea. So they fund his project. It's the first publicly funded, first government-funded private project. They're going to give him £7,000 per year, okay, to do this project. So in 1823, he starts designing the actual machine. But he can't build it himself, so he hires the best blacksmith in London, Joseph Clement, to actually make the parts. So he's designing the parts, and Clement is making the parts from the design. 9 years go by. British government's beginning to say, okay, where's our engine? And the British public begins to chime in with the same question. Where's this engine, as you guys were promising? So he goes to Clement and says, look, everyone's on my neck about this thing. Why don't you make me a little 3-column version of it so I can show these people that it's actually going to work? And so Clement takes 6 months off and builds this little 3-column version and gives it to Charlie as a gift. And he starts demonstrating it at soirees, and everyone says, hey, this really works. Is this the actual machine? It's kind of small. And he says, oh no, this is just a little piece of it. So they begin to call it the beautiful fragment, the little piece of the big machine. Well, the British government comes back the next year and says, okay, we've heard that you got this thing built. Let's see it. That's not the full machine, that's just a beautiful fragment. All right, how far are you on this right now? He's about half done. What does half mean? So, well, it's 24,000 parts, and we only have 12,000 parts made. And he said, wait a minute. We started this project 10 years ago. We've given you 17,000 pounds in this period of time, okay? And you're only half done? That's ridiculous. If you don't get this thing done pretty soon, we're going to pull the funding. Now, 17,000 pounds was enough to pay the 34 British people their annual salary. The typical British salary was £50 a year, £1 a week, with 2 weeks vacation. So that was basically how much they had spent on this thing. Now, if you go off and ask 34 people what was their annual salary over the last 10 years total, and add it all up, that would be how much money they spent in US dollars today. And I don't know what the answer to that is. I've never gone out and asked the question. Anyway, at this point, he goes over to Clement and he says, look, you're going to have to move your shop over to my side of the Thames River so we can get this thing done quicker. But by the way, I can't afford to pay you to make the move. Well, that kind of ticked off Clement because he's already had lots of troubles with Babbage. And he tells Babbage, I quit. I'm not going to have anything to do with you anymore. This is crazy. Well, British law says whoever makes the parts owns the parts. And Clement made the parts, so he's going to keep everything. And the British government steps in and says, no, you have to give some of the parts to Charlie because he designed them. So he gives him a smattering of parts, the ones that are of no consequence, keeps all the important parts, keeps all the tools, because there it is, keeps the plans that he's got, that he's been working on, Meanwhile, Babbage has got the other plans that have either been given back to him or he's working on. And they part ways. And Clement then looks at this metal he's got on his hands and decides it's not doing him any good in that form, so he melts it down and uses it for something else. He's not working for Charlie anymore. He doesn't owe him anything. So all Babbage now has is a smattering of parts, a beautiful fragment, his plans, and a dead dream. And the government pulls the funding. Project's over. But this doesn't deter Charlie. He turns his attention to a whole new project. He starts designing something that's 5 times bigger than the difference engine. He calls it the analytical engine. It's going to add, subtract, multiply, divide, do all kinds of sophisticated stuff, be programmable, okay, and stuff like that. And he starts working on that, and by around 1847, he suddenly comes to the realization he could have economized on his original difference engine. So he spends the next 2 years redesigning it. He calls it difference engine number 2. It's only 8,000 parts, 1/3 of the original 24,000. And when he's finished with it, he takes it to the British government and asks them if they will build that instead. And what do you suppose they said?
No.
No. Been burned by him once, they're not going to get burned again. So he goes home, puts the plans away, continues working on his analytical engine, keeps coming up with new ideas, never gets his design complete, keeps redesigning and redesigning and redesigning, and in October of 1871 he dies. Hasn't built anything. Okay. His sons inherit this stuff. They don't quite know what to do with it, but by 1875 they decide to give it to the London Science Museum. So the Science Museum gets the plans that Charlie still has for difference engine number 1, all the plans for difference engine number 2, the smattering of parts from the original thing, the beautiful fragment, all that stuff. And they decide they can't exhibit the plans, so they put all the plans down in the vaults in the basement, and they disappear from history. They're gone. And they don't surface for 110 years. Now we're not going to wait 110 years, but the crowd is so big, I'm going to split them into 2. So from about here back, you folks go to your left, and the rest of you just stay put. Go around to the back. You can go if you want. You're going to stay with him. Okay. So everyone back to the back. And meanwhile, you can center up here, and you're going to get a chance to go next. And we're going to crank it some more, you're going to see what's going on in the back. But they get to see first. Now I want you to
Give you guys a better chance to see what's going on in front.
Between the curtain. And come up close. Come up close. That's why we have the stanchions pulled up, so you can get right up close. Because you can't see this stuff. It's very, very small. Okay, that's great. This cave, and this cave. Between the steel pillars. On the blackboard, when I added 6 to 8, you said the answer was 14. Remember, the 6 counted down to 0. So I went like this, 6, 5, 4, 3, 2, 1, 0. Right? As it's turning, it's transmitting to the gear next door. That one's counting up from whatever number it has now. Okay? But it adds 8 to it. Okay? So let's say it goes something like this. It goes 9, let's say it's an 8. We already added an 8. We're going to add a 6 to it. So we're adding 6 to 8. So we're adding 8. 8 goes 8, 9, 0, 1, 2, 3, 4. So we're all done adding 6 to 8. 8 has turned into 4. 6 plus 8 is equal to 4. Is that the correct answer? That's not quite correct. It's correct in this digit, but it's not correct as an answer. 0 isn't really 0. It's 10. 9, 10. Well, what is 10? It's 0 where we are, and 1 on the gear above, added to the gear above. So we have to add 1 to the gear above. Does everyone agree?
Yes.
Okay. Except for the following problem. The gears are meshed together at all levels doing the add. The odd column is added to the even column, all the way up. You cannot interrupt the add to add 1 to a gear at random. So when it comes time to go from 9 to 0 and you want to actually add 1, you have to actually remember the fact that you have to do the carry. So he designs a bunch of mechanical levers that act as warning levers. He said, I have a carry pending and I'll take care of it when I get a chance. Okay, so the add goes through to completion and there are carry levers that are triggered as we go along. We finish the add. We lift that gear up in between the 2 columns and we reset the odd column. The even column, which got the summation, is now completely free. So we can interrogate the carry levels and see which ones have to add one figure above, because they're not doing anything at this point, they're free. But we can't look at all the numbers at once. Because if I add one to the gear above, and it's a 9, it turns and becomes a 0, it throws its own carry level. So we have to stagger the actual interrogation of these carry levels. And so he designs a bunch of spirals, looks like a DNA molecule. When you get back here, you'll see what I mean. Okay. So they go around, they interrogate the actual carry levers in a sequence. And you can actually propagate up to a series of 9 carries all the way to the top. Okay. These are the carry levers, these bronze things sticking out on this one, and on this one. You can see I'm touching them, they're sticking out. These are all flush with the steel fingers that are holding them. These are the ones that are about to get the carry levers thrown out.
What you guys will see on the front is
Once
it
they're
has
worn,
odd column and even
they
column.
get actually
And then
interrogated, they turn into
the
done.
number has to be restored to the odd column. Even column, there may be carries that get added in. And so if you watch the column that's not getting the restore, you may see some small changes as as individual wheels, sometimes a couple in a sequence, you add one to those numbers.
Ready?
Ready?
So we're going to see this first. Actually, you should watch those two. So trigger. Now these are going to reset. They're triggering up there. You don't know where to look. Back and forth. Fast. This is everywhere a moment ago. See, these all get reset. Now they're going to start to go trigger. Done. 4 or 5? 4. One more cycle.
One more.
The steel fingers come out and protect them. We trigger. We're done. Okay. Now you folks, you go to your left.
Yeah, so if you guys walk
And
around that way, to the back.
Continue left and get out to the front. If we had a bigger space, we wouldn't have to do this in shifts. Oh, I haven't gotten to that yet.
If you design that in
7 quarters always I'll get to that as to why that's the case. So stop, try to stay in the boundaries of that red curtain back there, because otherwise you can't see it very well. So scoot in and get up close. Shorter people up front, especially the kids. Let her up here.
If I'm too small.
No, that's okay. You get a good view of it.
Yes.
So, I'm going to get out of your way, Eric, and you can go. You've heard everything about this, but these are the levers here. So these are going to get triggered. These are reset. Now they're getting triggered. And then they get reset.
So it sticks out when there's a carry load.
They stick out when there's a carry, and then they stick out even further when the carry's done, and then they get retracted back in and start over again. So that one was triggered, and then it gets done, and now it gets retracted. First stage is this little bit out, like that, which is the warning, and then the second stage is they get done. That's all this is for. Propagation of carry. Nothing else. Yeah, the front of it's doing all the ag part. Okay, so let's get as many people. So let's get to the rest of the story. Paul Hartley used to say that, I think, right? Now the rest of the story. Come back out any way you like.
So how does it feel?
Now, somebody back there was asking me things like, what's it made of? We're going to get to that right now. We're into that last half of the story. Because what's happened is 110 years have now gone by. It's 1985. It's the year after the Macintosh came out. Put it in context. And Doran Swade becomes the curator of the London Science Museum. He goes to his technical staff and he asks them if there's anything there that they've got that they haven't exhibited. And they say, well, yeah. Down in the basement, we have all the plans for Babbage's Difference Engine and stuff like that. But they're not worthy of exhibit. So he says, well, I'd like to take a look at them anyway to see what they, what they look like. And they go down and look at Difference Engine number 2 and realize it's a complete set of plans. There's nothing missing virtually. So he thinks to himself, and says out loud, I think this could have been built in Babbage's time and that it would have worked. How can we prove it? And someone suggested they had the beautiful fragment so they could see what it's made out of. It turns out it's made out of cast iron, mild steel, and bronze. Very common materials. Okay? And they look at the workmanship of the carving of the number wheels by Clement. And he was achieving a 1.5 thousandths of an inch tolerance in 1832. So they go to the people who make these kinds of gears and they said, listen, can you carve these number wheels for us at 1.5 thousandths of an inch? And they said, oh, that's kind of sloppy. We can make them fit like a glove. And they said, no, we don't want that. We need 1.5 thousandths of an inch because that's all Babbage could achieve. Well, we can dumb down our machines and make them produce sloppy parts if that's what you want. That's exactly what we want. So they went ahead and decided to make another version of the beautiful fragment using Difference Engine number 2's design. And what they came up with worked, and it worked perfectly. So now they got the actual funding to start building the machine. And they started working on the engine part itself. Now by the time they get to the early part of 1991, they're almost done with the engine. And someone points out that December 26th is the 200th anniversary of Charles Babbage's birth. So if they can finish it in time for that, present it to the London public, it will be a real crowd pleaser. And that's exactly what they do. And London goes crazy because Babbage's engine has come to life. It actually works. Well, they spend the next few years demonstrating it in the London Science Museum, and one day, through the doors, comes Bill Gates. And Doran Swade thinks to himself, Gates has money and I need a printer. So he asks Bill, would you be willing to fund our typesetting machine, our printer? And Bill says, no, I'm not interested. But I know somebody who might be. And he gives them the name of his retired chief technical officer, Nathan Merrill. So they call Nathan on the phone, and they tell him that Bill suggested he might be interested in funding the typesetting for the Babbage Difference Engine. He said, well, I'm interested, but I have to see it.